Okay, everyone, in previous section 2.6, we looked at the graphs of some basic functions. Okay, now in this section we're going to look at some graphing techniques that show how to graph functions that are defined by altering the equation of a basic function. Okay, so these are somehow related to the basic functions. And remember the basic functions, just in a way of review, we talked about the identity function, we talked about the squaring function, we talked about the cubing function, talked about the absolute value, and square root of x. So we talked about these as our basic functions. Now, in this section, we are interested in some of the effects that we can again alter these basics and the effect on the basic graphs. What is going to happen to the graph? The effects that we are interested in are, for instance, we're looking at maybe there is a stretching or shrinking effect on the graph of the basic function. Possibly they could be a reflection of the basic function. We're going to look at those. And we're going to look at maybe there are some symmetries, right? So symmetry is important in our work. And we also eventually look at whether the function is even or is it odd, and its implication or effects on the graph of the function. And finally, when we're all said and done, by the time we get through this section, we should be able to graph functions using translations. Okay. And then later on also, I'll show you an example of all of these things in using a graphing utility, Desmos. So let's begin this one. For instance, suppose I have y equal g of x, and this g of x is related to the original function by means of multiplying f of x by a. All right, so that's one effect we're going to look at. The other effect we're going to look at is when g of x is going to be some form of the basic function, this time a times x within parentheses. All right. Now, if a is positive, for simplicity, for now, we're going to look at it when a is positive. We do take up the case where a becomes negative, the number outside and the number inside could be negative. What will happen is that a number that's negative on the outside or inside will cause some kind of a reflection. And we'll discuss those later. But for now, let's say, for instance, my g of x is going to be 2 times my basic function, the absolute value function, something that we looked at in the previous section 2.6. Now, 2 times absolute value of x, because the number is 2 times it. So if I look at, for example, here's x, here's absolute value of x, here's 2 absolute value of x. And if I look at the values here, just 3 values here. For example, when x is 0, absolute value of x is 0, 2 times 0 is 0. That's not going to change. But what if x is 1? If x is 1, well, absolute value of 1 is 1. 2 times that is 2. If x is 2, absolute value of that 2, twice that would be 4. So if you look at now the relationship between these numbers, absolute value of x and 2 times absolute value of x, it looks like twice absolute value of x makes sense, is twice as big. Okay, so it's going to be twice as large. So the on the graph, the implication would be this. Let's say here's my x-axis, 0, 0 doesn't alter. See, it's 0 for all cases here, for both cases of absolute value of x and 2 absolute value of x. So if this is the graph of basic absolute value that we looked at earlier in previous section, this multiplying the heights or the ordinates of the graph by 2, doubling the heights, that means a point that was here is now twice the size, is up here. This point that's that far is going to be twice as far, right? So it's going to be possibly up there. Now, and if I connect these dots together, So you can see now this is the graph of absolute value of x times 2, or 2 times absolute value of x. Same thing on the other side. That's going to be the graph of the 2 times absolute value for negative x values. So in this case, it looks like the impression that we get, the effect that we're looking at, it has some narrowing effect, right? This graph is narrower than the other one, 2 times absolute value of x. Remember, the one below is absolute value of x. This narrowing effect, visual narrowing effect, formally is defined as a vertical stretch. Synonymous with, there is going to be a vertical stretch. Again, the vertical stretch is going to give it a narrowing effect for the basic function. Now, what if this thing was, let's say, a value, suppose I want to do 1/2 now, right? What if I did 1/2 absolute value of x? Now the heights are going to be 1/2 what they used to be, right? So my graph will be dotted. There you go. That's what 1/2 absolute value of x is going to look like, isn't it? This one. And what if I want to do 2 times absolute value of 2x? Let's take a look at that one. So I'm going to make g of x. Let's make it go absolute value of 2x. Again, in relation to f of x, that f of 2x, where f of x is the absolute value function. All right, now if you look at the possible values here, let's say my x is -1, 0, 1. The absolute value of x is going to be 1, 0, 1. And absolute value of 2x, you multiply 2 times x, then take absolute value. So 2 times -1, -2, absolute value of that is 2. 0 doesn't change again, and 1 times 2 is 2. Absolute value of that is 2. So let's graph this one now. 0, 0. Absolute value of 1 is 1. Absolute value of -1 is 1 also. So this is going to be the graph of absolute value of x. Again, we've graphed this one in previous section also. So now what does absolute value of 2x going to look like? Well, for absolute value of 2x, when x is -1, right? When x is -1, it's going to be 2. So it's now up here actually. It's 2. And when x is 1, it's up 2 this way also. And at 0, 0 is like that. Now this one is hard to see. It looks like almost the one above, right? The vertical compression. But actually this one is compressed in a horizontal direction. The function that really look good for horizontal compression is going to be, they're going to be trig functions, but we don't cover trig functions in this course, in the college algebra class. Okay, and there you go. Again, it does look like the one above, right? So, and it does, indeed, absolute value of 2x is equal to absolute value of x. So the graphs are identical. This graph and this graph are identical. So we're looking at, this is what the horizontal compression looks like. Again, not a good example, horizontal compression, because it's so hard to see, because it literally looks exactly like the one above. But we can view it, it's kind of half full, half empty glass. The one above is half full, vertical stretch. The one below is half empty, horizontal compression, by a factor of 2. Okay. And now I'm going to generalize the effect of a on the function. So, if a is greater than 1, then the graph of y equal a times any function is going to cause a vertical stretch. Okay, vertical stretch of f of x, the original function, by a factor of a. Okay, that's what that would be. And what if a lies between 0 and 1? I didn't plot it, but there you go. That's between 0 and 1. Notice how the absolute value seems like those branches, the sides are flattening, they're opening up or flattening. So in fact, instead of narrowing, now we have a widening effect. Okay, that widening effect is formally known as a compression, a vertical compression. So if a is between 0 and 1, then y equal a f of x. This is going to be a vertical compression, which textbooks call it shrink, right? Shrinkage. Right up here, we have shrinking. So there's going to be a shrinkage of the graph, vertical compression or shrinkage, by a factor of 1 over a, not a, 1 over a. Okay, so for example, if a is 1/2, 1 over a half is 2, so it's going to be compressed by a factor of 2. Okay, now again, let's take a look at if a is greater than 1, and this time we're going to move a inside the function f of a of x. What would be the effect here? This one, although we saw a poor choice, absolute value I made, this one is going to be a horizontal compression of the graph of y equal f of x. And if a lies between 0 and 1, just like the case above, remember these two go together, these two go together, because our function is in different structure. The first pair, those a's on the outside, the second pair, a's on the inside. So that's f of x. Now we have a horizontal stretch, okay, of y equal f of x. Got that one? Now, what if a is negative? We look at the case in all cases, a was positive. If a is less than 0, actually, this is what's going to happen. Then we're going to get a reflection. Okay, we're going to get a reflection of f of x, the original function, about the x-axis. And the reason is because what used to be, for example, a positive value is now a negative value. Y was positive, now y is negative, means below the x-axis. If a is less than 0, and oh, sorry, I left something out. You get the reflection of if a is less than 0, and here I'm looking at a f of x. Then we're looking at graph of f a of x now. This is going to be a reflection of the original function f of x about the y-axis. The y-axis. Okay, so example of, for instance, the one that I just mentioned in the second pair, the first one. This would be like negative square root of x. And this other one would be square root of negative x. You see that? And I'm thinking, let me just formally make it. I'm thinking f of x is square root of x. So g of x would be negative square root of x. This one will reflect like so. This is the basic square root. The negative is going to look like this. There, that's negative root x. See on the outside? Reflection about the x-axis. And how about if g, let's go h of x, is root negative x. How is this graph going to look like in relation to square root of x? Well, this is the square root of x. Okay. Square root of negative x is now going to look like that. There. See the reflection about the y-axis. All right. And there we have this one. Now, let's look at, now that we've talked about these, let's look at other transformations. Okay, so we're looking at now transformations. With these transformations, we're looking at the transformation of f of x in the form of, let's say it would be a times f x minus h plus k, okay, of this form. So let's see, how is the effect of a, h, and k on the graph of the function? So first, if g of x, if we let g of x be f of x plus k, okay, an example, g of x is the square function plus 3. There you go. Just a number by itself, not mixed in with x, outside of x, the basic function. So for this one, if k is positive, then there's going to be a vertical shift of f of x by k units. And if k, my k looks like x, there you go. If k is less than 0, then it's going to be a vertical shift still, not a stretch or compression, but a shift of the original function f of x by k units. And because k is negative, we're going to go absolute value of k, because we're using the vertical shift. This would be up, this one vertical shift down. So the reason we go down absolute value of k, so we don't get into a double negative situation. Like for example, I say if you go down 2 units, then you're at -2, let's say. But if you go down -2 units, you're actually going up 2 units. The double negation here. So there you have it. That's the case. So for my example, if this is the graph of x squared, the basic parabola, x squared plus 3 will shift this up. All the points on the parabola will get shifted up 3 units. And there you go. That's going to be the graph of it. You see that? This is called the translation of the basic function, the squaring function. Now, let's take a look at, so this is vertical translation. Let's look at now horizontal translation. When you translate something, you move it. You move it up or down, right or left. That's the translation. Okay. Let's take a look at this time the translation of f of x in the form of f of x, and I'm going to go minus a number h. Okay. Now in this case, if h is positive, then the effect is a horizontal shift. This time horizontal shift is to the right, h units of the original function f of x. If h is negative, then we will have a horizontal shift, this time to the left, absolute value of h units of the original function of f of x. Okay, so that's going to be the translation we're going to talk about. To give you an example of this one, let's say for this one I'm going to have g of x is equal to, let's go absolute value of x. Absolute value of x minus 4. So in terms of the original function, we're looking at f of x minus 4, where f of x, the basic function, is the absolute value function. See, instead of x, I'm going to have x minus 4. So let's see what's the graph of this, what is it going to be? The basic square root function is going to be this one, right? This is absolute value of x. H here, and the reason I use negative is because that's going to help readability, and there's minus. Okay, so I'm going to look and see, for example, here h looks like, see, x minus h. That's going to be the h, correct? So h is 4 in this example. H is 4, which is positive. Well, if h is positive, then we have all of that. It's going to translate this to the right 4 units. Call this 4. And this is going to be the graph. You see how that works? And there you go. The graph of that. All right. And let's see. So that's what the translation is. Another example, let's say my g of x is x plus 3, this time again the squaring function. So for this one now, I can write it as x minus 3 squared, so it's in the form of x minus h. So you can see my h is negative 3 now. H is negative 3, which is less than 0. Going by what we have here. So there's going to be a translation of the original basic function, this time to the left 3 units, correct? So we're going to graph this one like so. Here's x, there's y. Okay, the basic parabola is going to look like this. Notice we don't plot points, by the way. I have not plot a single point for any of these graphs and not plan on doing it. If we do that, you're going to miss the point of this exercise, what we're doing, of the work we're doing. So this is my general x squared, right? We're going to shift that to the left 3 units, 1, 2, 3, and just redraw it. So you literally are cutting and pasting, or I guess copy and paste, there, depending on your point of view. So there, so let's say cut and paste. It's just when you copy, you have both of them. This is the final graph, by the way. This is just helping me graph it. So it would be a cut because it's no longer going to be there. So we do a cut and paste job. And there you have it. That's the effect of x plus 3. Now, all in all, we can put this together now. So the general form of our transformations are this way. G of x is going to be again a, f of x minus h plus k. And remember, if a is positive, actually, if a is negative, then we have a reflection about the, which axis? The x-axis. And there we have it. All right. So let me make up an example here. Suppose I'm going to do f of x equal negative absolute value of x plus 3. And I'm going to go plus 1. All right, so how is this going to work? We're going to start with absolute value of x. And as far as, again, the translations that take place, we can do them in any order. There's no particular order we can do this. It's really optional how we want to do it. So let's do absolute value of x. Absolute value of x plus 3. So I'm going to go to the left 3 units. Notice, by the way, positive 3, you go left 3. So it seems like contradictory, right? Or opposite, not contradictory, but it seems like opposite to what's inside the absolute value. Look at this one, for instance. This was x plus 3. We moved 3 to the left. So a lot of students tell me that helps them. So whatever it seems to be in parentheses there, once you put a number for h, do opposite of what that says. That's your h. So here's my absolute value of x. I can track what happens to this. This is going to move left, right? So at this point, I have absolute value x plus 3 is what this one is. The negative in front will reflect it, right? So we're going to have a reflection going in this direction. This is negative absolute value x plus 3. You see how I can track this step by step where it's going? And then we're going to shift this up, vertical shift, up by 1 unit. There is no compression or stretch, vertical stretch, because there is no number outside of the absolute value other than the one, negative 1, but I'm thinking absolute value of negative 1. So there you go. If this was, for example, negative 2 absolute value x plus 3 plus 1, now there is a vertical stretch, right, by a factor of 2. If that number was negative 1/3, there's going to be a vertical compression by a factor of 3. So this one would be exactly the absolute value. So again, we have the cut and paste, the idea of cutting and pasting them. And there you have it. So this would be this portion of the graph, and this would be the other portion of that graph right there. All right, and the solid line is the final graph here, by the way, right? This one, right? This and this portion. That's the graph of the absolute value. The key point that's in here, remember, is at negative 3. This point is at negative 3, comma, and we moved up 1, comma 1. So I usually track just one key point, 0, 0. What used to be 0, 0 here is now at negative 3, 1. Okay. And there you have it, the graph of the function. Now we can actually take a look at some of these through Desmos. So I'm just going to come back with Desmos open, and then we go through in order to help you see all these vertical compression, stretch, horizontal compression, stretch, and right shift, left shift, up, down, all of that. We're going to see it in a moment. Okay, now I'm in Desmos. Okay, we're going to take a look and see all of the effects that we talked about, the translations. I have them in this example. So I picked one of our functions, the squaring function. Okay, and remember the form is a f of x minus h plus k. So let's, for this work for now, I'm going to let a be 1. The coefficient is 1. Okay, so there's no reflection or vertical stretch, compression, what have you. So let's see what effect does k on the outside have on the function. Now, if you look at the parabola here, the graph of the parabola, I'm going to let the slider move, and you can see the effect of it. You see how as k becomes positive, there is a vertical shift of that parabola. You see that clearly you can see that much better now. And so that is what the effect of k outside of the function is. Just a number by itself. It causes a vertical shift of the original graph. Okay, now I'm going to stop this one at 0. There. Now I'm going to look at the effect of h. Remember, h inside will cause this parabola, this graph, to slide to the right and left. True. And if h is positive, it's going to move to the right. If h is negative, it's going to move to the left. So right now, h is going on the positive side. See? I'm sorry. Let me... Yeah. That's okay, because I cannot control the right, left. H is negative. If h is negative, it's going to move to the left. So check this out. So it's going to become more and more negative until my domain here is from -4 to 4. Okay, so check this out. As it becomes more and more negative, you see how the parabola, I'm looking up here. See, now it's becoming more and more positive. At 0, of course, then there is no shift. It's the original. But look, see how it's moving to the right? H is positive. So that is the effect of H. You have a horizontal shift. The translation is a horizontal shift, right, left, like that. And let me stop this one. And there we go. So both of these are now at 0. Notice I have the basic parabola. A is 1. Now I'm going to change A here. Remember, let's see. For example, A right now, A is 1. I'm going to make it 1/2. You see how the branch opened? Now I'm going to make it this one. I'm going to go in increments of 1/4. How's that? My steps. I'm going to go every quarter, so you'll see this a little better. Okay. So here we go. This is at A0. Don't worry about that one. So here's A is 1/4, a number that's between 0 and 1. You see how flat the parabola is? And then I'm going to go 1/2, not as flat. Okay, and that's this one. You see how the branch is closing in? Closing in, that's 3/4. At 1, it's going to become the basic one, right? There you go. Now I'm going to increase greater than 1. So I just went between 0 and 1. So clearly you saw that a vertical compression, right? Again, once more. There you have it. Now I'm going to go to like 1 1/4, number greater than 1. So this time now the orange curve is inside the other one. And then I'm going to go 1 1/2. There you go. See, there's a vertical stretch, which gives it that narrowing effect. At 2, there you have it. And now for negative values, let me choose a -1. This should be -1. Look at that. You see the reflection? So if A is negative, you have a reflection about the x-axis. And -1 1/4, -1.5, and so on. Again, you still have that stretch or compression effect. So now you're going to look at how this happens. You see that? So that's the narrowing, and that's the widening effect. Between 0 and 1, it's wider, and greater than 1, it narrows. And that's what we wanted to show. So you can put it all together now, and you get this crazy looking parabola that's moving all over the place. But that's not what we want to do. So let me stop this one, stop that one. So hopefully, again, I just wanted to show you how you can work in Desmos and get a better feel for this horizontal, vertical shifts and stretch or compressions. Okay, so we are out of Desmos now. Back to our note. Let's do our next idea. The next topic we're going to talk about is, let's talk about symmetries now. Okay, we're going to look at symmetry with respect to the axes and with respect to a point. So we're going to take up the idea of symmetry with respect to, first, with respect to the y-axis. So we're going to say that a function, the graph of a function, is symmetric with respect to the y-axis. This is if this happens. If you replace x with -x, then you get an equivalent equation. Okay, equivalent equation. Then that's a sign that the function is symmetric with respect to the y-axis. So for example, let's take a look at our basic parabola. If I change x to negative x, you square it, you get the original function back. So this function, the squaring function, is symmetric with respect to the y-axis. Okay, now what about symmetry with respect to the x-axis? In order to be symmetric with respect to the x-axis, this is if you replace this time y equal f of x with negative y, and you should get the f of x. You see that? So y and negative y should equal to f of x. Oh, let's try this one. Let's say, for example, I'm going to look at our relation x equals y squared. So if I change y with negative y now, negative y squared remains y squared, which is x. See, you get the same equation. So when you do that, that means this relation now is symmetric with respect to the x-axis. If I graph this one, the graph of x equal y squared looks like that, and you see the symmetry with respect to the x-axis right there. Now the graphs that we work with, by the way, you can see if there is symmetry with respect to the x-axis, then the graph of the function fails the vertical line test, right? And because we're working with functions, so seldom, if ever, we look at symmetry with respect to the x-axis. But this is a general discussion we're talking about. All right. Let's take a look at, for instance, another example. Suppose I have this relation. Notice this is not a function. This is a relation. Let x be negative x. Okay, so I'm changing x with negative x. Now I get negative x squared plus y squared equals 16. Negative x squared is x squared. Y squared, of course, not affected. And you get exactly the same equation. So this relation, again, this is not a function. This relation is symmetric, WRTO, with respect to. It's going to be symmetric with respect to the y-axis. Is it symmetric with respect to the x-axis? Replace y with negative y. So this time now I get x squared plus negative y squared is 16. And that gives me x squared. Negative y squared is y squared equals 16. And that is the original. True? That's the original equation that I got. Same as the first one. Okay, therefore, the graph of this would be symmetric, WRTO, with respect to x-axis. Now again, this cannot be a function because it has symmetry with respect to the x-axis. Now the last thing in terms of symmetry we're interested in are symmetry with respect, WRTO, with respect to, let's say, a point. A specific point for us is the origin. Okay, now we could have, by the way, we can do tests for symmetry with respect to any other axes, not just x, y. I can do a test for symmetry with respect to, let's say, line x equals 7. Those get a little more complicated, but this one, so we're looking at the basic coordinate system and a point, a very specific point, the origin of our coordinate system. Okay, so for this one, how do we test? Well, we're going to choose xy. Actually, not choose. Let's say I'm going to change. So fewer words involved. If I change xy to negative x, negative y, and you get the same equation, then that means the graph is symmetric with respect to the origin. For this one, let's actually look at our cubing function. We already have one in our gallery of functions, the cubing function. So for this one, I'm going to change x to negative x, y to negative y. So here's negative y. Say I change that. And then we're going to go negative x cubed. Change that. You got to change both of them, okay, not just one of them. So changing both, here's negative y. No need parentheses for that. Negative x cubed. Remember, that's negative x times itself. 3 times. That makes it negative x quantity cubed. It's going to be negative x cubed. Multiply both sides by negative 1, and you get y is equal to x cubed. Therefore, I got the original, right? I got the original equation I was looking for. And therefore, the graph of this will be symmetric. WRTO with respect to the origin. Origin is 0, 0 on the coordinate plane. And we've already seen the graph of this again in our previous lecture. On the previous section, the graph of this looks like so, right? That's our cubing function. Maybe this part there. Now here's the idea behind this work. If xy is a point on that cubing function, then right in here, negative x, negative y is also a point on that cubing function. You see that? And the symmetry is with respect to the origin. That's 0, 0. This other point, this one, has a reflection about the origin here. All right, and that's what that is. And for example, if I have a graph, let me just make a graph. Suppose my graph looks like this. For this to be symmetric with respect to the origin, well, it's going to look like that, right? This part of it. Again, this is a point xy, and that would be a corresponding point negative x, negative y on the graph of the function. And there you have that one. All right. Now, let's finish the lecture, not the video, but the lecture by the last concept in this section. This is a rather long section, a lot of ideas. Let's talk about even oddness of functions, even and odd functions. So, first, a function we say is even if f of negative x, change x to negative x, you get the same value of the function f of x. That's the even function. The implication of a function for us in this course being even is that the graph will be symmetric, WRTO, with respect to y-axis, the y-axis. What if the function is odd? Well, for odd functions, if you change x to negative x, you get negative of the original function. So that means on the graph would be this time symmetric with respect to the origin, not the x-axis, the origin. The graph of a function will never be symmetric with respect to the x-axis, because it will therefore fail the vertical line test, and that really defies the definition of a function. All right, so let's take a look at a couple of examples. For example, let's say my f of x, I'm going to make it to be this 2x to the 4th negative 3x squared plus 1, something like this one. You want to decide whether this function is even or odd. Okay, so what I'm going to do is I'm going to change x to a negative x, and let's see what happens. 2 times negative x to the 4th, 3 times negative x squared plus 1. And this is going to be 2. Now negative x to the 4th, that's x to the 4th. Negative x squared, that's x squared. Right, it's going to be positive. Look at this, look at the original. They're the same. If they're the same, then that means we just showed f of negative x equals f of x. And therefore, this is an even function. If we were to graph this, the graph would be symmetric with respect to the y-axis. Again, the even oddness have greater implications, especially in the field of integral calculus. When we go through integration process and so on, we can simplify the integration process, taking advantage of the symmetry of the graphs, whether be it even or odd, doesn't matter. But at this level, again, we are in a college algebra level course. We're just looking at the implications on the graph. Well, what implication does it have for the graph of the function? Here's another one. Let's try this one. I'm going to change x with negative x. So this time I have negative x quantity cubed minus 9 times negative x. And this is going to be, well, negative x cubed, again, we just showed up here earlier, right? I think I did. Yeah, right in here. Negative x cubed in parentheses is the same as negative of x cubed. True? So this is going to be negative 6 of x cubed. The double negative 9 times negative x becomes positive 9x. Okay. Now, if you look at negative f of x in here, what does negative f of x looks like? That's negative times 6x cubed, negative 9x, right? So, if I multiply by negative, now this becomes negative 6x cubed plus 9x. And you can see that these are identical. Therefore, or I can just factor it up here. Either way, that's negative of 6x cubed minus 9x. And this is the original. In parentheses, that is the original function. So, however you do it, we just showed that f of negative x is equal to negative f of x. Therefore, this function is an odd function. If we were to graph this function, the graph would be symmetric with respect to the origin. All right. And there you have it. Now, let's take a look at maybe just 2 or 3 examples here, and then we'll wrap up this video. So again, remember, I'm trying to keep these under an hour as much as I can, but sometimes I can't help because we got to cover a lot of stuff in a section. So let's take a look at this example. In this example, suppose I'm going to make my function the square root function. Okay. And let's look at the simple transformation of this one. So what does, okay. This is a graph of a square root of x. Keep that in mind. This graph we've done again before. This is in our gallery of functions that we know. Basic function, square root function. So what if I want to do the graph of square root of x plus 3? Well, this one, remember, x minus h. X plus 3 is x minus 3. So this is h. H is negative. So we're going to move to the left. And remember the way students work this, they say whatever this number is, if it's positive, your h is opposite of that. So h is negative. If h is negative, I move to the left. So you don't have to go through this process. Okay, and here is x. Now the original I show with a dotted line, or there you go, just use dotted for the first one, the original, that's root x. Root x minus 3, you move to the left 3 and redraw the same thing. There. Remember, you're doing a cut and paste. So that's the graph of it. We don't want to plot any points. Keep that in mind, please. Let's do root x, this time plus 3. See the difference? 3 is now outside. So this one is now going to be a vertical shift of the basic square root. This was the basic square root. Plus 3 goes up 3. And this is root x plus 3 now. What used to be at 0 is now at 3. Okay, there you have that one. What if I have, let's say, negative square root of x? Well, the negative in front will do a reflection about the x-axis, right? So this is the square root of x. And negative will reflect it. That's the final graph. Remember, the solid is the answer. The dotted is the in-between step. It's what's going to help us get to the final answer. So we have that one. And what if I have, let's say, 3 times absolute value of x? This time I have a constant multiple in front of it. So let's do this one. Again, here's the basic one, root x. 3 times means all the ordinates, the heights are triple what they used to be. Of course, 3 times 0 is 0, so this point 0, 0 isn't going to change. But this point, for example, whatever that is going to be 3 times the size now, right? It's going to be 1, 2, 3, like here. 3 times the size, and there. It's going to look like that. There is a vertical stretch by a factor of 3. And let's see, pretty much that's it. We can combine one. Suppose I want to do one that's like 2 plus root x minus 3. How's this one going to look? Again, this one is, let's say that's what root x looks like. Root x minus 3. Opposite of negative 3 is 3. So I go to the right 3. And then go up 2, 1, 2. So what used to be 0 is now at this point, and then redraw the dotted curve. There. And that's going to be the graph of this. Okay, so you see how easy that is done. It's really not that difficult. So we've done graphs. I think we've done enough graphs. Let's do another maybe even odd one. How about this one, an example? Let's say I want to do my f of x is negative x cubed plus 2x. Let's do f of negative x. So the question again, is this function even, odd? Now the function, by the way, doesn't have to be even, and it need not be odd. And if it's neither of those, then the answer is just that, it's neither. So I'm going to put negative x. Let's see what happens. Negative x instead of x cubed plus 2 times negative x instead of x. Again, negative of x in parentheses cubed is negative of x cubed without parentheses. And 2 times negative x is negative x. So this becomes positive x cubed because double negative makes positive. So this x cubed, oh, I dropped a 2, sorry, negative 2x. All right, now if you look at the original, it's negative. So let me tell you, at this point, does this look identical to that? No, it doesn't. One is x cubed, the other one's negative x cubed. But so let's see, what does the negative of f of x looks like? That's when you multiply this by negative. So it's going to be negative times negative x cubed plus 2x, right? That makes it x cubed. Distribute the sign, minus 2x. So isn't that negative f of x? Look at this one, look at that one, they're the same. So this is easy to do. This way you see exactly what negative f of x looks like. Or if you're into manipulating, like I can factor negative from the binomial here, and that makes it negative x cubed plus 2x. And that's the original function. Again, this is exactly what that is. All right, and there you have. So this function is going to be odd. We're going to say since f of negative x equals negative f of x, therefore, that's implication sign. That means this implies that the function is odd. And let's next take a look at some, again, just maybe 3 graphs. This will go fast. Let's say my h of x is going to be negative of x plus 1 cubed. So I have a cubing function. Remember my template, let me go back, a f of x minus h plus k. We're trying to see this structure into what's in there. So if I let my f of x be the cubing function, see underneath all this, I can see the cubing function, right, as the prevailing function. So it looks like, therefore, what does f of x plus 1 looks like, right, in here? F of x plus 1 is when you replace x with x plus 1. You see that? So you do have that x minus h structure there. And what else? Let's say the negative in front. The negative f of x plus 1, therefore, is negative, parentheses x plus 1 cubed. And that is precisely what now this function is. Okay. So, this is the cubing function. H, opposite of 1. In here, opposite of 1 is negative 1. So I'm going to have the cubing function that goes to the left 1, correct? Let me draw the cubing function first. That I'm going to use a dotted line. Right? That's x cubed. This one is x cubed. Plus 1 actually shifts h is negative 1 here, right? Opposite of 1 is negative 1. So you go left negative 1. Redraw this cubing function. That's at negative 1 now. And then a negative will reflect it, doesn't it? Right? Negative 1 is, this is negative 1. There. Now we have a reflection of this graph. What do we reflect it about? We're going to reflect it about the x-axis, correct? So when we do reflect it about the x-axis, that would be this part, and this would be the other part of it. That's the final graph. This is h of x. So shift left 1 and reflect. That's all that is. And again, I want to emphasize, we do not want to plot points. You never saw me do this in this section at all. So we don't want to really do that at all. Now, let's take a look at another couple more that will make it go fast this time. Suppose my f of x is 2 times x minus 2 squared, the squaring function, minus 4. Now for this one, we can see the effects that we have. Here, we have a horizontal shift, right? H is 2. Opposite of negative 2 is 2. So h is 2. If h is 2 greater than 0, we shift right. So the basic function underneath is the parabola, right? That's the basic function, x squared. We're going to shift this to the right too. And there you have it. That would be the shifted version. Shift right 2 times 2 will, remember, it will do a vertical stretch by factor of 2. The vertical stretch greater than 1 gives it a narrowing effect. And of course, minus 4 is going to drop it down 4 units, right? Now that narrowing effect, because I'm not using a calculator, as long as I make it this narrow, so you see clearly the narrowing here. So this is x minus 2 squared, and this one is 2 times x minus 2 squared. And minus 4 is the last effect. I'm going to use the narrow version, drop it down 4 units. And there you have it. Here is the narrow version of the basic parabola. Okay, this was the basic one, x squared. And we can actually report one point. The key point here is going to be 2, negative 4, which we call the vertex. So that's point. The point that we trace is this point, the low point of the parabola. All right, so hopefully you were able to follow that one. And let's finish this one. I've got I know I'm at 1 hour, but this will go fast. It's going to be 2, let's say root x plus 1. The effects of this one, what is it? We have the square root function. 2 will scale it, right? By a factor of 2. Stretch it and shift it up 1. Okay, so there you go. That will be the graph of this one. So it's not too bad, right? We're able to finish this fairly rapidly. Okay, that's it. Again, please review the parts that you may have issues with. Remember, the idea is transformation of the original function. That's what we want to do. We want to transform the original function, and that's what we did. So we are done with this video. So sorry, I went a minute over our intended hour long. Thank you for watching the video as always.